data. So it's great. I'll give you more example. Suppose that we have this tree. So you have 10E here, 2D here, 2C here, 2B here, 1A. So 1, 2, 2, 2, that means 7. So add up, this root node of the subtree is 7. 7 plus 10 is 17. So you have this whole tree. So suppose that after this figure, there are more A coming. And how does it affect this tree? So there are more A coming. So the first A, we make this A from the weight 1 becomes 2. And we need to update this from 3 to 4, 7 becomes 8, and so on. So we need to update the frequency accordingly. So it's still fine. Everything is still fine. And then when you have one more A coming here, from 2 becomes 3, that's where the problem starts. Because like when this 2 becomes 3, let me explain. So in the original adaptive Huffman, as one of you guys asked before, what's that label for? That label is to make it easier, such that you make descending order from the top to the down, from the right to the left in a descending order. So they try to make it such that at no time that in this descending order, you will have the weight further down in this order will have higher weight than the one further up in that order. So it means like if the weight of this A keep increasing, I should really swap with a node with higher label number with the same weight before I increase the weight. So in this sense, it will somehow skew the heavy weight to the right-hand side and top. Okay? So I swap the A with the D because A will from 2 becomes 3. So A will be higher frequency than D. All right, so it's right here. And then the next thing, A will keep increasing. But when A increase becomes 4, that's still fine. But look at what happened when A becomes 5. This intermediate, so this subtree here, the total weight is 4. A right now is still 4. But if I add one more to this A will be 5. So A should be more popular than this whole branch. The idea here is that if A is more popular than the whole branch, you will penalize that less popular branch, push them down, because you are actually more popular. So you can see that if the distribution of the weight is a bit more even, you have a more balanced tree. If they are skewed, one is very popular, one is less popular, the less popular will further down in the tree. Answer some questions before I give you guys a toilet break. Question? Yes?
Should A, when the third A comes, should A replace B, or if it is possible to like shift B from 2, 5, or sorry?
It's swap.
Yeah, just swap the.
Correct, just swap. Other questions? So very soon, guys, means that we only have BWT left. So after the break, when you come back, it's just like very short time. It's the correctness of Wikipedia. After you come back, I show you like where's wrong. And then after where's wrong, then part 1 of BWT. That's it for today. It wouldn't take longer than 35 minutes. So let's have 9 minutes break.
Just a quick question.
Sure.
So this tree lives in the memory,
Yes.
right? And it seems to me that the decoder needs to use this tree together with this tree.
No. The decoder, so this tree is constructed in the encoder and decoder. It's the same tree. So in the decoder, when you get this one, you start with this. So when I see this one, I know it's a new A. I will still move from here to there. We will have exactly the same tree.
Ah, right.
It will be exactly the same tree.
I was curious, but why D and B cannot be under A?
A is a leaf node. It contains a symbol. It cannot be a middle node. It cannot be under. Only leaf nodes store the data. You can't.
Oh, it can't be the middle.
No. It's a Huffman tree. You can't. In the actual Huffman tree, only the leaf nodes store the symbol.
Where's the not transmit in this graph? Is it this place?
Yes. I don't know. Somewhere. It's not important
I
because
think is the smallest ID is the not yet transmit, right? And if the ID increase, the weight will increase.
yeah. But this example only show part of the tree. There may be some other thing not shown here, which only show part of it to show you how the rotation works.
Okay.
Yeah.
Sorry, I just wanted to ask. I don't really focus much when it's like lecture and like in live, but like I go home always rewatch it, and that's when I really understand. So I was wondering, could I just like be watching? Because I never skip the lectures. I just watch them at home. Could I just do that instead of coming in?
I think so, except the discussion part, because
Like the discussion part is just
it's
like
not properly
asking
captured.
questions
Yeah, or explaining only that part.
yeah,
Otherwise,
kind of, and just watch it at home. Because I can't really, I just keep spazzing out, and like in lectures at home I can just like rewind.
yeah. To see how it goes, you may want to try until maybe I don't know, like this lecture or next lecture, and then you can make a decision. Because the first lecture is supposed to be probably the easiest of the whole course. This one is not now. I mean, after the break, that part is the hardest.
Right.
And also the next week, the first part of the next week is harder. Then the rest is more normal.
Balanced.
Yes. So you can decide after that.
Alright.
But other than, as I said, the discussion bit, I don't see a big problem. But if you can't participate in the discussion.
Right. Okay. Alright. Thank you very much.
So first we got A, we don't need to put like point fixation like with 0. Because this is
The first A, yes.
So we don't like 0 and 0.
No, because when you get the first A, you have this one. This one, there's no 0. 0 means like this.
With the choose number.
Yes, the tree. This one doesn't have number. No
doesn't
number.
have number,
yet.
so
So it's nothing.
Okay.
Yeah.
In the case that any of these add one more, obviously then W there will be bigger than W there. Will that change anything, or will it stay the same then? I think it should stay the same.
If you add anything down there, and if you add a lot such that the weight of that will be even larger than A or something, then they will swap back.
Right, but the weight of E is 10, and the weight of that whole subtree is 10. If you add one more to that subtree, that doesn't move that subtree, does it?
If you add more to which subtree?
Because I mean, because 2, 5, 4, that weight is the same as E. Right? If you add one to any one more of these, any of these, make that 11.
No. You will make that 11.
Yeah. They
Left and right. Left and right.
They will split. Okay.
Yeah, it's the same as like I said before the case that because they try to maintain, because this label is 255, that's 254. Always try to lopside to the right hand side.
Yeah.
It was full. It's a very good question.
Yeah.
Okay, guys. All right. Let's resume. So it's a bit confusing when you look at if you try to do the Google search. That's just for your information. When you try to look at the Google search, you search for adaptive Huffman. There are two versions. One is from 3 people called FGK. The other one from Jeff Ritter. So there are two versions. So it's FGK and Vita. So we are going to focus on the Vita one because the Vita one will give you more a balanced tree. So to explain the difference, so I need to briefly let you know the difference. So you know roughly what the difference when you look up in the internet or when you try stuff, you find out how come it's different than what Raymond said in the lecture. Because there are two variations. So first is the FGK. Suppose that you have this tree in the memory, and when another F is inserted, while F is right here at the moment, so you have 1D, 1G, 1C, and 2F, and this is all their frequency distribution. So if I insert one more F start with 111. So my bad. So start with 1, I insert one more into F becomes 2. So essentially, you just increase the count here, and that's it. As long as you still maintain it such that the frequency closer to the root node have a high frequency. The least probable one is further from the root node. You are fine. Now, the Vita version have more invariance. The FGK have explicit node numbering. The Vita one is implicit. As one of you guys asked me before, how can I label the node? You can label the node any way that you like, as far as is the number is decreasing from the root to the bottom, and from the right-hand side to the left-hand side, you are fine. Whether the numbers start from 1 million or 256, it doesn't matter, as far as they're decreasing. It's implicit. And another variant is like, for each weight W, all the leaf nodes of the weight W precede in the implicit numbering. In that numbering we talk about, all the internal nodes of the weight W. If the internal nodes and the leaf node have the same weight, you want to make it such that the leaf node will precede the internal nodes in that implicit numbering I'm talking about. So I'll give you an example. This example is like, why Jeff Witter want to do that? Because Jeff thought of that, if I do the adaptive Huffman, I will have this case. This case, like, suppose this is a normal static Huffman tree. I have 2A, 3B, 1C, and 2 spacebar. And when I form the Huffman tree, I get the least two probable one, which is C and a spacebar. So frequency 1 and frequency 2 add together become 3. Now, the next thing I'm going to do, I have choices. I can get this A, which is 2 and 3, or this 2 and that 3. If I get this 2 first, I will have a deeper tree. If I get this 2, it's more balanced. Right? It's either skewed or balanced. Depends on which one you pick. So this like slightly, I don't know, gray line or blue line here is the choices I have. I'm not going to link all of them, but you can link this side first or that side first. Okay? It will give you an equal weight. Now, to do that, if you do the left-hand side first or the right-hand side first, it will give you a different outcome. Although, when their weights are the same, what does it mean? It means the total number of bits required will be the same. But it's a different tree. But the total number of bits is the same. So you have a preference. Now, this one, if you choose this one, is more balanced because all of them require 2 bits. This one is more skewed, but the total number of bits are the same. So you can't do the adaptive Huffman. If they have choice, I can choose this one or that one. You need to standardize it. Otherwise, you can't decode it because the encoder and the decoder may choose a different preference. So you need to impose some variance. And Jeff Witter decided, I want to have the tree that's more balanced or more symmetric than skewed. So he do that by impose the invariance. So this is from his paper, which you can, I will put it, you can download it. So instead of having that one, the space bar, the C, the A, and B, and so on, you will tend to have this one instead. By the way, this 0 is an NYT, not yet transmit. Now, how to do that is here. This is the Wikipedia thingy. So the problem is right here. It's a very small problem. Are these the same weight, 1, 1, 1? They are the same weights, right? One of the invariants said that all the leaf nodes should precede the internal nodes according to this labeling, this implicit numbering. So means these 2 should be swapped. When they swap, if you look at that, if you look at the labeling, like starting from the bottom to the top in an increasing manner because from the top to the bottom is decreasing. So from left to right, increasing. Now you see all the leaf nodes first before you see the internal nodes. I know this is a very minor step in Wikipedia, but if you keep constructing the tree like that, you will get a different tree. Now this is the correct one. You just need to swap them. If you don't swap them, that's not the Jeff Witter tree, which is the page said that it's Jeff Witter, but it's not. Again, if you have free time, other than your assignment, by the way, it's not accessible. It's like I won't give you marks if you're going to correct the Wikipedia page, but if you want to do it, you can. So, this is exactly copied from the paper. You have the paper. It's just saying that in there are two cases, case A, case B, and in the case A, node P, this one, the square one is a leaf node. And so if this leaf node right now, so in this case, the leaf node have the frequency 4, or the internal node is 4, and then 5. This is in the order of the numbering, implicit numbering. So when I try to increase this 4 to 5, what I'm going to do is like, I will shift or swap, when actually it's shift in a Witter case, you shift this, you slice it and insert this into just before all the internal 4, because you're going to increase this 4 to 5. Slice it in front of all the internal 4, increase this number from 4 becomes 5. Then you finish this, this operation. You look at the tree according to the labeling number and make it almost like an array right here according to the ordering of those numbers. And you shift it in that way. Is it easier or harder or more confusing? Is it more confusing? Ignore the slide. Come back here. It will be exactly the same as what you have so far done, except that, as I said, the Jeff Witter case, except that when you have equal weight, you put all the leaf nodes on the left-hand side and further down before the internal nodes, if they have the same weight. Otherwise, nothing changed. It is just trying to differentiate this situation I mentioned to you before. With the Jeff Witter algorithm, it would prefer the right-hand side rather than the left-hand side. Okay? Question? You don't have a question? I have a question for you. What's the difference between adaptive Huffman and static Huffman? Of course, you can tell me that, oh, one is static, one is not. Great. What's the difference between their performance, like the outcome? If I give you the file, let's say I don't require dynamic Huffman, adaptive Huffman. It's static. I give you the file. And you use dynamic one, adaptive one, and a static one. Will give me the file the same, become the same size, or one will be better than the other? If you don't count the overhead table.
Well, I think the advantage of dynamic would be if different parts of the file have different frequency distributions, and it should adapt to that. Whereas a static one would use like an average for the whole file, which is probably not possible.
Good answer. So what happened? Is it like one is always better than the others, or not necessary, or some cases, or depends, or what? So you're saying some cases one will be better than the other? What cases?
If you have, like in the case that we saw, if you have a massive repeated pattern, one will end up better than the other because you will use more bits depending on the tree that gets built throughout.
But if you have one of the A, they repeating a lot, let's say extreme distribution or skew, then in both cases, that node should be very close to the top, wouldn't it?
Over time, but it might take some, depending on where it is in the file, it might take some time to get there.
Good, good. Yes.
It matters more on the frequency, if the frequency changes. So like if A is really common at the start, and then afterwards in the second half of the file it's not as common, and then like B is really common, then it's like, you know, the what's it called, the bit character will change to adapt to that.
But then for the static Huffman, you have an advantage. You can scan the whole file first. So if you know the whole file first, will you be able to make a better decision if you hold, like you already know the whole frequency?
I feel like if I average out, now that I think about it.
Average out. So average out, what do you mean? Mean the static better or what? Or in your situation, which one will be better?
In my situation where the first half is like mostly A's and the second half is mostly B's.
Yeah.
In the static, I feel like there'll be like some midpoint where like A and B will be like maybe 3 bits each, whereas in the adaptive, A in the first half, A might be like 1 bit, and then B might be 4 or 5 bits, depending on other distribution, and then that will flip in the second half. So it sort of, like I said, averages out. Like the static will be the midpoint.
Great, great, good, good, very good. So compared to the static case, dynamic, I mean, the adaptive Huffman is dynamic and can actually offer better compression ratio. You are right in the sense that if your distribution, as you said, like it's various, and the static case, as you already mentioned, is overall, it's only taking care of the overall statistics. But if there's a trap, like at the beginning, actually that one looked like actually popular, at the end it's not popular, but you capture that local statistics advantage to optimize that first, because you may have a shorter bit length locally for that group of character, and later change it shorter to the other group of popular characters. So in that sense, it's more adaptive, and you get better performance. So that means what? That means if you consider the overhead of the statistics table plus this kind of more localized adaptiveness, in most of the situation, you will have better performance using the adaptive Huffman. Then what's the catch? What's the issue? The issue actually is you as a programmer. You have a high complexity to implement that program. Unfortunately. Yes?
With the dynamic one,
Yeah.
So say like there's a whole file,
Yeah.
and there's say 3 sections. One's got, the first one is lots of A's, the second one's got lots of B's,
Yeah.
the third one's got lots of C's.
Mm.
Wouldn't A be the most popular, when you get to the B section, A will still be the most popular?
Yes. So if they're just equally popular, then at most B will be as popular as A. But before B take over A is still the most popular. Yes.
Yeah.
Yes.
So with dynamic, are you just taking the last, say, 100 or 1,000 characters, or are you taking it from until the very beginning?
Dynamic or static? You want to talk about dynamic?
Oh, dynamic.
The adaptive Huffman? No, it will be so far at this point.
Right.
Which one is the most popular? Because the tree is keep changing. So the popularity only counts as of this point.
Yeah, but you're trying to get the minimum of a certain area, right? That's the point of dynamic.
Yes, yes,
Right.
yes.
But you're not taking the minimum of a certain area, especially when you do at the end. You're taking the
No,
minimum
no.
values of
So
everything, you know what I mean?
so it only happens, for example, let's say like you have A, B, C.
Yeah.
A started with quite popular, but in fact O4 is not the most popular. Then you have B. B actually more popular than A. But before you see B, A is the most popular. But after you've seen B, B is the most popular. Then later, after you've seen C, C is actually the ultimately most popular. Then in that case, if you have the overall static Huffman, you of course give C the shortest one because it's the most popular. Then even A is less popular than B and C, but still quite popular at the beginning. You wouldn't give the shortest one. But when you started with, you will try to give A a shorter one. Later, oh no, B is actually better. It's like you're seeing, girlfriend. You see one. Oh, that one's even better. Oh, this is even better. So before you're saying it, you thought this one is the best. So you have that local advantage. But if they're equal, no, it wouldn't. Yeah. So it works when you don't have statistics at all, so it's good. It also saves the symbol table overhead. There's some experiments he did, and you can get it from his paper. So it's just like he using the funny symbol. So T is the total number of symbols in the source message. K is the number of number of distinct symbols in that message. And ST here is a static version of the Huffman. D is a dynamic version of the Huffman. And this one is a total size, but excluding the overhead, such as the symbol tables and the leaf node. This just count the internal nodes, not the actual leaf node of the ASCII code and so on. This one is including the symbol table and overhead, but it's the bits per letter. So if you're using this one, for example, it's 13.1 bits per letter. That one is like 10 bits per letter, including all the overhead. That's why it's longer than 8-bit, because that's including the overhead. So when you have totally 96 distinct symbols and the file is slightly larger than that, means that the file contains all the unit symbols. And they are very close, almost like equal probability. So that is what happened in this encoding. So you can see this is static, this is dynamic, and if you look at the bits per letter, that's what happens. The bit per letter is a dynamic case, actually is much better in that sense. And then you look at the next one. Now, the number of distinct symbols are similar, but the number of symbols of the file is getting more and more. So then you can see the change. So at least you can see that the dynamic Huffman or the adaptive Huffman is not worse than the static version. And yet you don't need to know the statistic beforehand, and it's adaptive. That's it. You just need to know one adaptive case. You can handle the situation when people give you a file but don't give you the statistic. It's a streaming file. You know what to do. Do the adaptive Huffman. Quite popular. Any question? No, then I can't wait. This is the exciting part. Question? It's the exciting part. We can finish it in 10 minutes. So exciting, so we can finish in a very short time. BWT. Now, I emphasize that again, BWT is not a compression. T stands for transform. It doesn't make things smaller, but it wouldn't make it larger either. It just transforms. So how it transforms is, as I try to inspire you in the first lecture, is when you have the string like the first line, it transforms into the second line. of the same length. It doesn't compress, but it's not make it larger either. When it transform becomes the second line, then you can compress. Using running coding, whatever, you can compress. But certainly, the second line is easier to compress than the first line. Okay? All right. Now, to do this BWT, a simple example. Now, in case you don't know, your lecturer have lots of favorites, such as bananas. I like bananas a lot. You know, all the nice strings I like. The funny, all the repeating substrings I like. Bananas, Mississippi, Kiwi Billy, you name it. If there are lots of repeating substrings, and I love them. So let's start with banana. So I purposely put a hash in front of banana, so when I concatenate the strings or where it is, you know where's the beginning of this string. So it's like nothing special, just mark where's the beginning. So you have hash bananas. All right, let's start to do BWT. First step, step one, can you do all rotations? Rotation means like you rotate this string one letter at a time. So say, assume they wrap around. So you move the last character in front of the first character. So you move S becomes the first letter. And then move A becomes the first letter. Move N becomes the first letter, and so on. Can you do that? We call this all rotation, step one. Okay? Can you do step one? No question? Great. Then step two. Can you sort all these rows? Just a normal string sorting. Sort them alphabetically. Just sort them. So it means like, assume hash is before A, then hash, this line will be before all the lines start with A, then all the lines start with A will be before all the lines start with B, all the lines start with B will be before all the lines start with N. If they are both start with N, then NAN will be before NAS. It's a simple string sorting. Can you do that? Great. Last row is BWT, that's it, done. No, last column. Two steps. That's the output. As I said, you ask me why, but why is harder to answer. How to do it is easier, two steps. Why it has to be next week? Because it takes longer than that. Yes?
Algorithmically, like, when you actually do this, would it be like kind of hard to like store all you copy, all the rotations would be n times?
That is a very good question. That's why I said that like you actually don't need to store them. Instead, you have a pointer for them. So you don't need to store them because each row is only have a different starting position of the string. They are the same thing, just different starting position. You don't need to, yes, you only store the starting position. That's it. It's not much to store. Yeah. So now the take-home exercise will be, you can start with this one. So first, do this one, find all the rotations, sort them. The last row, the last column will be the second line. Yeah, but sometimes using hands are just more fun. All right. In fact, not now, because you can tell that even you can do this, to do all rotations easy. To sort them, it still takes some time. And it's hard to do, I mean, you can say, yeah, to sort them, it still takes some time. You know, n log n for sorting, and it can be very long, so it's not nice. And to do it by hand is even messier. I think 2 or 3 lectures from now, we will talk about the algorithm that can do this in linear time. Means like, I can work this out by hands in less than 10 minutes. So, but that will be 2 weeks from now. That's a linear time. So, but let's talk about a dummy one. Dummy one is not that dummy. It's easier to remember because only 2 steps. The step is like, find all the rotation, sort them, last column. You can remember that. It will work, and that is BWT. So it will make it like that. Now, so as I said, I will explain why it's like that next week, but for the algorithm, the step is only 2 steps involved. Now you will tell me, if I get this SBNN hash triple A, so all the A together, all the N together, how can I get back my favorite bananas from here? So you can reverse this process. How to reverse this process? That's how you do it. The input you have is this SBNN hash AAA, which is similar. You can get the second line as the input. You want to get back the first line. So when you get SBNN hash AAA, all the same letters are mostly together, and you want to get back to the original strings, how to do that? Not hard. First, add them into your memory. Okay. Secondly, can you do that? Sort them. Again, row by row, sort them. So after you sort them, it will be hash first, then A, then B, then N and S. After you sort them, add your input again, as in concatenate them again in front of them. SBNN hash AAA. Sort them. Add them again, 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 sort them. You get it. Banana. You can't not to know the steps, as I said. But as I said, I make my promise in the lecture 1, the steps are easy. It's 2 steps or 3 steps, and they are very simple steps. But to understand why it works, gosh, it will take a lecture. So that would be next week. Now, when you, in the next few weeks, you'll see much larger file. Those file will be a database or some DNA or some biological files or sequencing and so on. It will be gigabyte of them. Those gigabytes will be very similar to this example you have seen, like the first line. And after you run the BWT, it will actually group all the, the same characters together continuously. And then you can do lots of compression on top. It gives you very good compression ratio. So next week, I will explain why it works, and you will understand exactly why it works. And then the week after, I will tell you how can you search on this transformed space to find out the substrings of the original strings without converting back to the original strings. Now, I'm not just telling you how to search them. I will tell you searching in this space is ridiculously fast because it's constant time. I can tell you how many CAB, C-A-B, in these strings in constant time. Even there are 1 billion CAB there, I can tell you in constant time. That will be after next week. Then the week after, I will tell you how to do it by hands in 10 minutes. Questions? Just to give you some preview, in case you want to know, that will be related to your assignment 2. But so far I haven't put the 10 minutes construction in any assignment, because by doing that, it will be a disaster for me to scale up the student marks. And I don't want to, because that's really hard. That's insanely hard algorithm. It's not hard to explain to you, it's just so hard to implement. So sometimes you will see the algorithm, they're really elegant, they're actually very fast, even you do it by hand is fast. But somehow when you implement it, it's just very hard. It's very hard. And they are constant time, but that constant is a giant constant. You laugh now. It's still constant. So it means like, constant means like, if it takes 1 hour to do 1 gigabyte, to do 1 kilobyte, it might still take 1 hour. That means constant, but it's constant. I can show to you it's constant. I can do it by hand, and everything is constant. And you will understand exactly what I said in a few weeks' time. They are constant, and you will agree with me, they are. It's just you don't want to implement it. Any other questions? Now, so far, at least for the BWT, okay, before BWT, I hope you understand all the material. I try my best to explain to it. But for BWT, you do not need to understand why it works, as far as you know how it works. Like the steps involved, you can do it, that's fine. Next week, I will tell you why it will work. And that is very hard to explain and for you to understand. So that will be next week. Okay, guys. See you next week then.
Yeah, it's a tunnel. I can do that. But I thought you were getting the vote. Yeah, first.
No, that's constant, not infinite. That constant is it's not too bad, but practically it's okay too. They actually use it like practically like for DNA like sequencing.
But if you have like hundreds of gigabytes, is it like it's like instant though to a person like?
It is fast, but as I said, like for normal consumer use, they may say it's slow, damn slow. How come for like 10 megabytes it takes an hour? But as I said, even for 10 terabytes it'll be an hour. For 10 petabytes it will be an hour. But yeah, you got to have. I suppose you have a hard drive that can hold that data. Will give me like constant time I/O. So everything it has to be constant performance. But they do that for all the like US and so on for the biological lab, and that's how they do it. It's exactly the same algorithm they use for search. It's just a huge constant. So if you do it for high-end computing, it's worth it. But I wouldn't do it just for a couple of pages of Word document. That's not worth it.
Yeah, I see. Okay.
But it's a constant. It's not as bad as I exaggerate. You can implement it probably like every time it takes maybe the constant. We'll talk about 5 minutes or 10 minutes, but I won't use it for Microsoft Word. When I do like search or find next word, it takes 10 minutes. Don't let me use it. As I said, for DNA sequencing, it's brilliant.
Yeah.
That's the one that they use to crack the DNA coding. So it's brilliant.
Wow, that's so cool. Like first course that we're gonna learn something, and it's like that's what they use.
Yeah, that's what they use. But of course, they make.
And it's pretty much the same for like these bows. We learn combining that with Huffman and stuff. If I'm using WinZip or something, it's pretty much like what they're using, isn't it?
The next lecture, I think I will give you some. Like you can do better than that. I mean, anyone from this course can do better than WinZip.
Nice. All right, awesome. Thank you very much.
No worries.
Thanks, sir. Have a good day.
You too. go first. You can go first. I want to talk about some questions. Okay. Do you want? Yes, you want. Yeah.
Have a nice day.
You too. You too. You guys have more questions? Any more questions, guys? No?
No question?
No? All right,
Maybe
good.
next week, after you explain that,
Sure.
why it works.
Sure, anytime.
Professor Wong.
Yeah.
So you are teaching the final project as well, 990.
Sometimes.
Yeah, like what exactly is it like? So I have no idea like what to do in that course.
It's a good project. I mean.
So the project will be given. It's like a specific project, or is it like open-ended?
You better. I think you don't need to worry about it until when it happens. Because it's slightly different. I mean, the principle is the same, but slightly different depends on who teach it. So
yeah.
I only teach like one. I mean, as in one.
One cohort.
I only teach 2 courses per year. So this one I definitely teach. Then the other one is either the project course or the database that comes 9311. So it's either one. Depends on the school. So if I'm teaching a project one, it will be give you some project choices.
Yeah.
But the project choices only have minimum requirement. There's no requirement, only minimum requirement.
I see.
So then the project team will pick the minimum requirement and extend it.
I see.
So when they extend it at the end, different team will come up to present their project. The core will be the same, but all the ideas are different.
I
The
see.
core are the same.
The core.
Yeah, and then we have people like the tutors, and sometimes will be some guest lecturer and myself, a few people to give the score based on that.
I see.
Yeah, so it's like a project implementation.
So the lectures are not that content, it doesn't have much content, like the weekly lectures.
No, it's not. If you look at the handbook, it's not a teaching course. So it's more like a project course that the lecturer is to make sure that the course is running in a fair manner, as in like all the team members are contributing and no one cheating, and not like, it's not fair, like this guy do so little work, he got higher marks than me or something. So it's like managing courses, projects rather than teaching. They do have like 2 or 3 lectures in total, but it's just like in case of some people never done any projects before, they give you some methodology or approaches how to deal with problems. You don't learn much of that. You learn more from your team instead.
Yeah, what about if I implemented some projects beforehand, and then like maybe it happens to be compatible with the core concept?
Then you're lucky.
Then we can just expand
the idea is like, you're lucky, I can only say that. It's just, you're not supposed to do that, but you can't stop you do that. But the idea is like we assign you some minimal requirement of project choices. It's to avoid someone have done that before.
Oh, I see.
And put it in. It's to avoid that. But if you do that, unless you tell us that, otherwise we can't stop.
But it really depends on like how hard the project, like different difficulties of different teams, like they will get different marks, right? Like,
they will
even
get
based on the same core.
They will, but your choices is not like many choices. Usually like 2 or 3 or 4. So that means each project will have at least like 5 or 10 teams doing similar stuff.
I see.
So then they can compete and so on. And also each lab they will have a tutor to see and give you feedback. The tutor pretend to be your customer or something. So there's some interaction, there's some record. So it's all about managing project and people and the team and a fake customer. It's all like it's different than other courses, but it's practical, but it's not a teaching course.
Looking forward to that. Thank you very much.
Welcome.
When you add some language, you will see that there will be collector, another, which short term is a word.
If the hash is in the end, you get the same like the original result. If the hash is
Of course, you can try. Yes.
you always put the hash in multiple.
No. If you push the hash at the end, of course, the answer may not be the top because then the string will start with B, right? Bananas, something like that. Then B will be somewhere between. But you will know which. So at the moment, later I will teach you, but at the moment you are sure that you know the hash at the beginning because you want to know that where's the beginning. If the hash at the end is like a file, end of file symbol. So you can assume the hash is the end of file symbol.
Okay, sure.
Then every file will have a symbol called end of file.
Sure.
Then you put it there, you sort that. The line, the last character is end of file, that's your answer. After you sort that, the line, then the end of file is at the end, that's your answer.
So you need to know what is the character you, how to say it? Okay. You know that that's the end of file, so it should be at the always at the bottom.
Otherwise, after you have done this, the only thing we know is that one line is your answer. You don't know which one.
Exactly.
Yes.
So how do you know which one?
The line, in this case, the line with the first letter is hash in this example.
Yes.
In the other example for the file, it's a line that the last character is the end of file.
All right. If the file doesn't have the end of file, you stop.
Which file doesn't have an end of file?
I don't know. It's like some corruption file. Then.
They still have an end of file. Any file must have an end of file. Other file will not end.
Right. Interesting. Yeah.
The definition of end of file means the file end. Can you give me a file that doesn't end?
I was thinking different like media file that doesn't have end file.
Media file have an end of file. Media file have an end of file.
Okay.
You will be able to find at least one unique symbol. That's the end of file. Sometimes you find more.
But if you're streaming, right, you get a bunch of bits. There's no end of file.
This one doesn't work on streaming. At least the discussion. You need to have whole string. It's not